We're good? My name is Kevin Kilgallen, and welcome to eFAB Expo. We're bringing this virtual show to you as a representation of a typical trade show. This afternoon, we're going to take a look at Miller Robotic Welding. The idea here is for you to get ideas to improve your business. And when you think about welding, finding welders can be a challenge, training welders can be a challenge, but once you can fixture some of your parts, the productivity of a automated welding process versus a manual process is phenomenal. So please continue the journey with us as we go down this aisle at our trade show. And I'm going to turn this over to Miller Welding, and here's Dave Schaefer.
Hello everybody, my name is David Schaefer with Miller Welding Automation. We have a little video about the robotic welding solution that we have to queue up here for you, and then after that I'll show you a little bit more technology we have for offline programming. I'm here to explain Miller Welding Automation line of PerformArcs pre-engineered systems. These line of systems are here, they're pre-engineered systems to help you get a high productivity with the lowest risk in the marketplace. So in this system, this is the PerformArc 350S. The 350 stands for payload, so you're allowed to have 350 pounds per station. The S stands for servo indexing. So I'll explain what indexing means here real quickly, and you can see how fast this machine indexes. So once I go to auto mode, I step out of the light curtains. It won't index if I'm in the light curtains, so I have to step out of the light curtains, start in auto mode, and press go. This system has about a 2-second indexing time. So that means once you step out of the light curtain, it has about 2 seconds to index in. If you notice the robot's running in the background, it's welding in station B while I'm out here unloading and reloading station A. I'll spin that again. You can see I'll break the light curtain while it's welding. The robot's moving in the back. I'm unloading one part and loading the next part in here. Robotic welding beats manual welding. The rule of thumb is about a 3-to-1 ratio, so you can get about 3 times the production with robotic welding than you can with manual welding. The big reason you could do that is because you can keep the arc lit about 80% of the time, and that's due to the fact that you're unloading and loading the next part while the robot arc is lit. That keeps productivity high. If we come around this side of the system, we have full sheet metal sides of this machine. When I open the door, you can see inside of it, everything's palletized and attached, either welded or bolted to one common base. It has fork runners that run along the whole base of the system. If you look inside of it, you can actually see why we can spin this machine and index machine so fast. We actually use a full Panasonic servo positioner on its back that does the indexing. So although it might be a little more expensive to do that, it pretty much makes the indexing just about bulletproof. The servo machine will react very quickly to whenever you break the light curtains. This is our TM1400 robot. Miller Welding Automation uses Panasonic welding robots for all their pre-engineered PerformArcs systems. We have an option to have the torch either go conventional mount, this is called conventional, or through the wrist torch. This wire would be tilted down a little bit and the torch would go through this hole, up through here, and then right through the wrist. So with the same robot, we have the option to go conventional or through the wrist torch. If we keep walking around the cell, everything on the back of the cell is mounted still commonly to one common base. So you can see we got a welder. It's the Miller Auto Continuum 500 welder. We got the transformer here. The transformer is the incoming power for what we need at the system. We have the controller of the robot, and all these are mounted. You can see they're bolted down. So none of this is going to shift. This tile system can ship to you in a box truck. The heaviest part of the system is in the back. So when you open the doors to the box truck, this side is facing you. You just take your fork truck and pick it up off the back of the box truck, lift it up, lay it down to your floor. You lag it to the floor, all you need is wire, gas, electricity, and you're pretty much going to be ready to go with our pre-engineered PerformArc line of systems. You come up here and look at the PLC cabinet. You see it has our placard in it, which has our address and our phone number. This is our phone service supply number. It's a 24-hour phone service number. When you call them, you tell them what model you have, but then also what's really important is the serial number. The serial number of this system is J2175. We call them job numbers. That means this is a 2,175th system we built. So that means that all the small little nuances of buying a one-off system is gone and engineered out of it since we built so many iterations of the system. If you look further down, it says exactly when it's made, February 2020. And it also has several part numbers, your torch part number, your drive rolls, your contact tips. A lot of your common usage parts are going to go into this placard, so it's really easy for you to reorder from us to what you need. We go further down in the controller of the robot system here. You see our preventive maintenance tag. You come over here, and just for an example, you come over and say, all right, I'm running 8 hours a day, 8 hours a shift, and I got 5 days a week. So if I say 8 hours a day and 5 days a week, I'm in the green. If we look over in the green, we say you got to change your batteries every 2 years. You got to re-grease the robot every 3 years and inspect your welder every 2 years. Mainly making sure your connections, your weld cables are tight, and you want to blow out the machine to make sure any dust that gets in your welder has been blown out to keep it clean. Makes it real easy and handy dandy for people to know exactly what they need to do and when they need to do it for proper preventive maintenance. We keep walking around. The machine comes with a service disconnect on it already for electricity. The machine standard comes with a 460 volt three-phase input power. It's already pre-fused. So all you do is feed us electricity from your bus bar, and we take care of the rest of the power that goes to the system. And then once again, both these doors, when you're programming, both doors need to be open. And when you're running an auto, both doors need to be closed. This is a torch reamer. About 98% of the systems we sell come with a torch reamer. It's already pre-programmed when you get it, when we build the PerformArc system for you. The torch comes down and clamps. The torch reamer, the blade spins, goes up into the nozzle to clean out the spatter, then comes over here to an anti-spatter spray to get the spatter, help clean the spatter off your nozzle, and it also helps cool down your nozzle. Then it comes over here to a wire clipper and clips your wire to dress it and give you a proper length. We also have a TCP tool check. So if your welds are ever out of the joint, you run our pre-program when they build the system again. This program is pre-programmed to come over and put the wire right over the point of this TCP check. If that's off, then you know something happened. Chances are your torch might have been bent from crashing or something like that. If we take one more walk up to the front of the system, I want to show you how this machine reacts quickly to an error if we break the light curtain. So when I do this indexing again, the fact we use that servo motor, when I come in here and it indexes, watch how fast it just breaks and stops once I break the light curtain and how easy it is to recover. So this is about the distance right here from the spot of the center divider spinning. Once I break the light curtain, you see how short of a distance it is for me to break the light curtains and walk over and load a part. We have one of the shortest distances in the industry. And once I clear the light curtain, you see how easy it is for me to restart the system. Voila. It's hard to find manual welders out there. I'm not sure if you're aware, but AWS did a study a few years ago, and the average age for the human manual welder is about 54 years old. We don't see as many young kids getting into welding these days. One thing that I'd like you to know about robotic welding is it can give you a 3-to-1 payback, a rule of thumb payback on robotic welding relative to manual welding of 3-to-1, meaning that you can get the same amount of production out with a robotic welding system like this, a PerformArc 350S, than you can take for it takes 3 manual welders to get to. Okay? Not only that, the robotic welding system is much safer than manual welding. When the operator's out here loading this system, he's away from the welding arc, so he doesn't get the arc flash in his eyes that you traditionally can get from manual welding. Plus, he doesn't have the fume inhalation problems that you get from traditional manual welding as well. People normally put a fume hood over the top with the fume extraction system. The operator is out here away from those fumes. So he's loading and unloading the system, pressing the start button and walking away from it. So he's not exposed to the traditional safety risks that you'd have for smoke, fume, inhalation that you'd have in the past. Also, robotic welding is much more repeatable than it has been in the past. The robotic system that you see here, the Panasonic TM1400, has a repeatability down to 1/10, 10% of the wire diameter that you're welding it. So when you see a manual weld and you compare it to a robotic weld, a lot of times you can tell just by the aesthetics and the consistency of it that it's done robotically instead of manually. So there's several things that help justify and give you an idea how robotic welding is going to benefit your process. As I back up, and I take a piece of steel, clamp it down. This piece of steel is bent, so you kind of see I just bent this a little bit ago. Clamp it down in the fixture. Now imagine if your part moved a little bit. In this case, this is a little bit beyond what you probably see in the real world, but if it moved a little bit, you'll see exactly what the system will do. I run the exact same program, and you see how it gets feedback from the welding system, basically the amperage to follow the height of this system around this bend coupon. You can see the weld follow the contour. The robot followed exactly the height. You can see at the same time it was calculating what was happening with the arc to give you very little spatter. It followed that height automatically. That's basically a demonstration of auto extension, which is auto height control. So when you're MIG welding, you're robotically MIG welding, you want to make sure that when you spin the part in for the robot to weld, that it welds completely and then spins back out without any problems. A common problem that a MIG welding robotic system has is when the robot comes down to strike an arc, it feeds the wire down to the part and gets a better contact at the tip of the wire than it does inside the contact tip. That has a tendency to arc off inside the contact tip and melt away and burn back to the contact tip, and then you get shut down. The operator has to leave what he's doing in the front of the cell, open up the system, detach the wire from where it's burned away, take the contact tip out, replace the new contact tip. He's down for 5 minutes. So Panasonic developed this system called Lift Arc Start to help eliminate that as best as possible. Lift Arc Start, basically when the wire feeds down and touches the part, the communication between the robot and the controller and the welder is so fast that as soon as that wire touches, the robot physically lifts up to create the air gap at the tip of the wire and not inside the contact tip. Thus your arc starts at the tip of your wire, not inside your tip. Thus you don't have the burnbacks that are traditionally happen in robotic welding systems. So I'll demonstrate this. I'm going to do 4 little spot welds here. You kind of watch the robot as it comes over here. In the beginning of the weld, it does a lift arc start. It also does a lift arc end to make sure the wire isn't stuck inside the puddle after it's done welding. Hello everybody, back to David Schaefer here live. Another demo I want to show you besides the ones we just showed you on the live welding demos there is what we call Dtps, Desktop Programming Software and Simulation. This is offline programming, so I'm right now at the PC and my laptop, which you can use and load in any PC. You can load a 3D model of your part, which I have one loaded up here. You can see I can put it in this virtual world. What's nice about this is I can simulate for somebody remotely and virtually their part being welded in one of our robotic welding systems. And the times that we're in right now, a lot of times, on-site visits and the social distancing that we want, this goes a long way into showing somebody exactly what we can do on your specific part in one of our robotic welding systems. So this is the exact same system that I had loaded up before, that I showed you the demos on, the Performarc. This is a little larger one, the 750, but similar action with the flat table. You can see once I have it programmed, I can spin it around. You can look at all sides of the system. And I have this one already pre-programmed to run a demo. And there you can see it run through the motions. I'll run through that one more time so you can see it clearly. It's welding vertical down, and then does 4 tacks on the top. So using this software, if you're able to send me a 3D model of your part, I'm able to put it in this 3D world and basically give you a nice simulation remotely so you can exactly see how your part would be welded and how the robot would move around it. I'm going to switch back to my front camera. And then we can do some questions here, question and answer.
Great, thanks, David. We will start. Oh. Dave, you still with us?
Can you see me? I have to reconnect my phone once I change my
Perfect.
camera.
Great. Hello? Well, we do have a few questions coming in from the chat.
Great.
All right, the first one here. Oh, pardon me, wrong screen. What are the pros and cons with a conventional versus through the wrist for the welder?
One of the biggest ones, I guess I'll walk over here next to my system a little bit here. Probably the main benefit that you really get from the through the wrist torch, you can kind of see, I don't have the through the wrist on this one, but I'll explain a little bit more with the through the wrist, is when you have the conventionally mounted torch, you have your whip, the back end of your torch up here, flopping around, okay? So what happens is when you go to a through the wrist torch, if I can show you a little bit more over here, that back end of that torch goes through kind of the inside of the forearm right here. So all this whip now is held so it's not flopping around. So that's basically the pro in my mind. That's a good benefit of having the through the wrist torch relative to the conventionally mounted torch. When you switch to the other one, there are reasons why you still want a conventional torch, which is what I have here. A big reason why you want a conventionally mounted torch still is when you're doing a lot of small boss welds. Means if you're going to do a lot of small 360 welds. It might be a little hard to see on the camera here, but the bottom of the tip of the wire is like directly below the 6-axis of my robot. So if I'm doing small 360-degree welds here, it's much easier for the robot just to turn this 6-axis here to do those small boss welds 360 degrees than it is for the through the wrist torch to articulate through small little 360-degree boss welds. So really it's application dependent. The longer robot you have, the more I recommend going with the through the wrist torch. The shorter the robots you have, the more you might want to go with the conventional. And then the application really dependent, which really has to do with if you're doing small 360-degree boss welds, for example, the conventional torch in my mind would be much more suited to that application.
Excellent, great. Here is another one coming through now. What is the largest part size that can be welded on this system, and is there other versions designed for larger parts?
Yes, this system is a Performark 350S. If you look at the table, I'll kind of zoom out a little bit again on the table. You can see that some of that well. This is basically when it spins, it's almost like a record turning, like a record player. This diameter that you see that our witness area here that's in yellow is defined by 60 diameter. So you have to 66 in a record. You can almost think about it as a record. Take that 66-inch diameter circle, and cut it in half because you have your center divider here. That splits that 66 diameter circle in half. So it's hard for me to exactly say what size part you have. Whatever part is going to fit in half of a 66-inch diameter circle in the system. And yes, we do have larger systems. The larger systems we have a 750S, 750SW. That goes up to a table that has a 108-inch table on it. And then overall, we have 9 different Performark systems. Some other systems that we have positioners. So if you need to take your part and you need to turn your part and rotate it, we could actually put positioners inside the system. We eliminate this table and put a head and tail stock in here to turn your part. There's different iterations of that where the head and tail stock goes all the way up to 144 inches, 12 feet head and tail stock, and up to 70-inch swing diameter, means like the width of your part. So there's several more iterations of systems that can handle larger parts besides this one. And we can talk further beyond this virtual fab tech if you'd like to learn more about what larger systems may be suitable for your specific parts.
Great, excellent. I'm glad. I'm sure a lot of our customers will love to kind of meet with you later and discuss some things. But we do have another question here. I'll put it on the screen.
how long does it take to set up for a new part run, i.e., if you have various parts that need to be welded?
A lot of that would depend on some of your fixture changeover. So I guess there's two things that you got to think about when you're doing changing your part for robotic welding. There's the first step that would be developing the fixture and the programming for that part. Once you have that completed, then all the difference, the time it's going to take is how long it takes to take off your last fixture. Maybe I'll show this again. You know, whatever your fixture is to weld a specific part, you'd have to take that off and put the fixture back on it. That may take somebody maybe a half an hour to do the change, and then you just change a program in the front of the teach pen. That is only going to take about 10 seconds. But if I back up a little bit, if I'm going to do a little estimates, it's always going to be dependent on how difficult your part is. So a development of a fixture, just a design of it, that can take, you know, that may take a couple to build the fixture. For a part that's the small part that I showed you that demo on, that Dtps offline programming demo, that specific part, I bet you it would take, I would say probably about 20, 30 minutes to program. But programming the fixturing, like I said, it'd probably take me 20 minutes to 30 minutes to swap to then rerun that again in the future.
Great. We have another question coming in here. I guess I would be able to do all the programming from my PC. Is that correct?
Is that what it says there? Okay. So on the Dtps software, the virtual world is only so perfect to the real world. So there are some calibration activities that we can do as we build the system to make it as accurate as possible. But when you program in the virtual world, the fact that it never matches the real world exactly, there's a couple extra steps. Well, you actually program the robot just a little bit out of the joint. So you program the robot in your virtual world about a half an inch to maybe an inch out of the joint until you get more familiar with how accurate your model actually is. And then when you actually put it on your system and you load it into your system, you actually step through it in the real world, and the fact that it's out about a half an inch to an inch out of the joint in the virtual world, then you go and you dial in exactly in the real world. We've gotten much better in the recent days to get that as accurate as possible, but you're never certain how accurate your model is to match your real world system until you start doing some iterations of loading your program and then seeing how close it is in the real world. So you can do the majority of your programming on the Dtps offline programming world, but I don't want to have any false pretenses where it's exactly going to be perfect and there's no touch-up needed. But it probably saves you doing the programming in the virtual world and then doing the touch-up later. It probably saves you a good 80 to 90% of the teach pen time that you would normally have programming a part from scratch on the robot system itself.
Great. And this is our last question here, Dave. Can you do a study of my part to see how they fit up in process as a feasibility study?
Did it say actually fit up?
Oh, sorry.
How they fit up.
How they fit up. Yep.
Yeah. So fit up is one of the two things to really be careful for to make sure your parts are really adequate for robotic welding. One is the joint being located in the same space every time you put another part in there. The rule of thumb for a joint location is half the diameter for being repeatable to sit in the fixture, because a robot's always going to go to the exact same place in space. When you talk about fit up, that is what we would describe as like a gap condition. So if you have a weld joint that has a nice tight fit and then you get a gap condition there, the rule of thumb for fit up, i.e. gap condition, is half the thickness of the thinner member of the two pieces of steel you're joining. That's only for steel. Aluminum is a little bit more less tolerant than steel is for gap conditions. Fit up is a little bit more difficult to understand without actually welding, 50 parts in a specific fixture that's made, because you never know what your repeatability is going to be on parts and gap conditions without actually welding the parts. What we do have is people to send their parts to our lab, and normally want to have about 10 parts sent to our lab, and you want to recreate a sample of the fit up that you're going to have and what you're really going to experience inside your shop. So when we send those to the lab, we can do some real world welding on those parts that you send us in the lab to exactly see how tolerant the weld process we have on your fit up. But but it'll get you about 90% of the way to see how applicable your parts are for robotic welding, because, you know, like I said, you'd have to want to weld 50 or 100 parts to really see how accurate it is. The best thing to do too is, as well, is when your manual welders take parts that are fabricated and put it in the fixtures you have now, take a look and do that measurement of that half the thickness of the thinner member that you have, and maybe make a feeler gauge and do some measurements of your current gaps. And as long as they're less than that 50% the thickness of the thinner member you're joining, chances are you'll have a good robotic welding process. Like I said, in the actual welding that we can simulate, we can send it to our lab in Chicago for actual welding of your parts with a robot in our lab.
Great. Well, thank you, Dave. On behalf of Mid-Atlantic Machinery, Southern States Machinery, Northeast Machinery Sales, thank you for joining us for eFAB Expo. We appreciate your time, and all the customers out there viewing. You will all receive a link in your email if you want to schedule additional time with Dave and Miller Welding. Our next session is Tiger Stop at 1:30 p.m. So we will see you over there.
Thanks, everybody.
Bye, Dave.
Thanks.